Ladies and gentlemen, to the first press conference of the European Space Agency in 2011 on the occasion of the presentation of the first data package and the first scientific results of the Planck mission. My name is Markus Bauer from ESA Communications and I will moderate this press conference. Allow me to set a little bit the scene. 13.7 billion years ago the universe sprang to life with a big bang. And in the first fractions of the first second of its life, the universe expanded dramatically at a huge factor. But 1 second after the Big Bang, it continued to expand and it cooled down. And it was only 380,000 years after the Big Bang that it was cold enough that neutral hydrogen atoms could form. And that was quite significant because simply matter and radiation separated. And it was for the first time that the first light could travel through the universe. And this first light is called the cosmic microwave background. And Planck will actually deliver to us a very, very accurate picture of this first light of the universe, which will allow us not only to understand how the universe looked like 380,000 years after the Big Bang, but also to compare it to what we see today. So there's a lot of information that will tell us about the evolution of the universe and about structure formation. Now, there is a downside, a small one, because the microwave background is radiating in other wavelengths that other sources of the universe are also radiating. So we have a kind of source radiation that we have to eliminate to really get a clear picture of the cosmic microwave background. And Planck is able to see those radiations as well. And what we will do and what has been done today is that these sources, which are of scientific interest by themselves, we have been putting them together in a catalog, and the product is called the Early Release Compact Source Catalog of Planck, which is one reason why we do this press conference. And the other reason is that there are scientific results connected to these sources, and this we are going to present to you as well. Our first presenter of today will explain to us what is the role of Planck for cosmology, but also for the space science program of ESA. It's the head of the Science and Research Support Department, Mr. Mark McCaughrean. Is the beginning?
No, you need to be on the beginning first slide. Okay. Thank you, Marcus. Good afternoon, everybody. It's a pleasure to welcome you all here today on the first scientific results from Planck. And my role this morning is just a very brief introduction to where Planck sits within the context of the European Space Agency Space Science Program with its partners, its national and international partners. And of course you know that there are a huge number of international partners, national partners, member state partners, institutions and members from around the world involved in Planck, and you'll hear more about that later on. But again, I will talk to you a little bit about the context which we find ourselves in. And I wanted to start with just a slide showing you a list of the operational ESA space science missions today. There's a large number, an unprecedented number of missions in operation, and in fact we've just recently at the end of last year extended many of those operational missions out to 2014. These are in date order of launch from the bottom up to the top, and the ones in purple are the ones we're actually building for implementation. And today of course we're only going to talk about Planck in great detail, but I will touch on a couple of highlights that we had from last year just to set the context again, set the scene for where we are this year entering a new year. And again, we have a series of missions which are not astrophysics at all, but planetary missions, and those were in the previous chart. And one of the great successes last year was of our Comet Rendezvous mission, Rosetta, which is on its way to a comet with a rendezvous in 2014, but last year had a flyby in the summer of the asteroid Lutetia, the largest asteroid so far flown by a space mission. And the scientists have discovered many exciting results about this rather peculiar asteroid, some of which have been made public already, but there'll be many more results from this in the coming months. Switching to astrophysics, astronomy, we cover the electromagnetic spectrum, as you can see in this diagram here, from the high energy with integral on this side here, all the way round to where Planck sits, which is in the radio to millimeter and submillimeter regime here. And we have a whole range of missions in between, studying the universe in very many different wavelengths, but also for very many different scientific purposes. And one of those great successes, and this was a highlight of last year again, is the Hubble Space Telescope, now in operation for 20 years and continuing to operate perhaps for another 4 or 5 years in this decade, maybe even longer. The last servicing occurred in 2009, of course, and Hubble has had this benefit of having its instruments upgraded routinely. So even though it's a relatively small telescope today, it's actually very powerful scientifically still. One thing that Hubble has done a huge amount on is studying star birth, star formation, and the birth of planets in our own galaxy, but also throughout the universe. And that's a unifying theme for today in a way, because much of what we do in modern astrophysics is actually about star formation and star birth, whether individual stars with their planets or galaxies full of stars. And so Hubble has participated in that very strongly, not only in these nearby regions here, but also in images like this, which are very familiar to many of you, the ultra-deep field and the deep field images taken by Hubble, where you're probing the history of star formation and galaxy formation in the universe with redshift. As you look at the fainter red, smaller red dots in these images, these are the objects which are further back in time. The light has taken a long time to travel to us. We're seeing them as they were younger when they were vigorously forming stars. And that's something you'll hear about with respect to Planck today. Planck's take on looking at star formation in these early galaxies. And these galaxies look here to be more or less randomly distributed across the screen, but that's not true at all. Galaxies are distributed in filaments and structures, which was imprinted by the cosmic microwave background, or the cosmic microwave background shows you the origins of those structures, which galaxies live in today. And so again, what we know from these images and what you'll see from Planck today illustrates how galaxies evolved over cosmic time and in the structures they evolved in. Now, what was launched in 2009, along with Planck, of course, was the Herschel Space Observatory, extremely successful observatory alongside the extremely successful Planck. And you've seen a bunch of images in the last year from the release that we had in April last year from Herschel. These are just some representative pictures of, again, star formation in our own galaxy. So these are regions of star birth ongoing today, which Herschel has the spatial resolution to start resolving individual protostellar clumps and looking inside those regions. And this illustrates, again, something you'll hear about this morning. These same star-forming regions, Planck has a story to tell with respect to the dust grains which live in those clouds. So you'll hear more about that again this morning. At the same time, Herschel is able to look at the distant universe in the same way that Hubble has. It has not the same spatial resolution at this longer wavelength, but every one of the dots in this image is a galaxy in the universe. And these galaxies are forming stars, and we know from the results from Herschel and other satellites that and ground-based data as well, that they're forming more stars the further back you look in time. And again, you'll hear about new diagnostics on that particular star formation rate, building of galaxies in the large structures from Planck. So here is Planck. This is a pre-launch image, of course, with the cover over the main entrance reflector there. And Planck's role is to look fundamentally, to look back here, as Marcus explained, at the cosmic microwave background, 380,000 years after the Big Bang, the first imprint of structure as matter and radiation decoupled. But we have to look through everything else in order to see that. And you can see in this representation here that galaxy clusters are forming over time and the structure is evolving. And again, we're learning about how galaxies form into clusters. And Planck has a very neat technique for looking at how galaxies are forming in young clusters in the early universe and in the nearby universe. And we can look, therefore, at how they evolve in time. So again, you'll hear about that with Planck. I just want to finish with a little illustration of where Planck has taken us. This is a slightly small personal anecdote. When I started my first postdoc position back in 1988, this was in the US at Goddard Space Flight Center in Maryland. And this particular satellite, the satellite which took this image, COBE, was just about to be put together, finished down the corridor. And I was working alongside John Mather and Mike Hauser and people like that, who then later on launched COBE and took this very famous image of the anisotropies, the deviation from the perfect black body, which illustrates the first structures forming in the universe. This is COBE's image of that. Subsequently, we've seen the results from WMAP, another NASA mission which has much better spatial resolution and therefore and more sensitivity, able to resolve these structures better. Planck goes beyond that. Planck introduces a factor of 3 more spatial resolution, and resolving these little structures and being able to understand their so-called power spectrum, how they're distributed across the sky, is a very important diagnostic on how the very early phase of the universe began, how the so-called inflation period, which Marcus alluded to, took part in forming these early structures. And so we have 3 times the spatial resolution, 10 times better sensitivity, because Planck is a fully cryogenically cooled mission, so better in that regard than WMAP, and also covers a much wider wavelength range, a frequency range, 9 frequency channels, which then enable us to do much better science, and you'll hear about that from the scientists that follow me. And this is the image which you've seen many times, and you'll see again today. This is Planck's image of the same sky, but with the foreground in the way now. And this foreground is the stuff that we're stripping away in order to be able to see the CMB in the background. But of course, as Marcus said, there's much science to be done with the foreground, not only in our own galaxy, which you see here, but also even out in these regions out where the CMB is. There's information to be gleaned there as well from the Planck data. This is to illustrate that this is the galaxy. These are some of the familiar objects, Orion, the Magellanic Clouds, the galactic center, and these play a role, these sorts of objects, in the results you'll hear today. In the general sense, star-forming regions are our own galaxy. And I just wanted to finish by showing you that, again, this is the whole sky, but Planck's data is much better than this. This is, if you like, a low-res image to fit it on the screen. But if I focus on this small part here, which is the nearby star-forming region called a fucus, I'll zoom that in and you'll see how good Planck's data is. Exactly the same piece of the sky, same data set, now zoomed in. And the quality of the data are absolutely astonishing. And I think we're all very proud within the Space Agency, but within the European community and internationally, about how well Planck is doing. And we continue with Planck. Planck will be taking data now for at least another year. In its full mode, and then beyond that as well with just the low-frequency instrument. So it's exceeded expectations enormously. So with that, I'll finish, and we'll pass on to the speakers who will describe the science results.
Thank you very much, Mark. Can you hear this over there? The next speaker is Fabienne Casoli. She's the head of space science and exploration of the universe at CNES. And Planck has 2 instruments. Mark said it already. There's an instrument called low-frequency instrument, and the other one is high-frequency instrument. They cover wavelengths between 1/3 of a millimeter up to a little bit more than 1 centimeter. And there have been major space agencies and institutions contributing to the development of those instruments and also to the data center, because Planck really creates a lot of data. And the major ones are the French Space Agency CNES, the Italian Space Agency ASI, NASA, and then in the UK it is the Science and Technology Facilities Council, and it's the German Space Center DLR. Fabienne will tell us now the involvement of CNES and the role Planck plays in their space science program. Thank you.
Thank you, Marcus. As Marcus said, Planck is an ESA mission. I think you have understood that. And in the missions of the ESA science program, the role of member states is usually to provide the instruments and to support the data analysis. And this is what France has done in the case of Planck and mainly in the case of the high-frequency instrument, HFI. Où est-ce que je clique? Okay. Okay, I just want to highlight a few of these contributions. Okay, you have seen many times this first all-sky image, and maybe you are not aware of what is behind this beautiful image. The main part of the main contribution is the detectors of the high-frequency instrument, which has been provided by the US, but these detectors need to be cooled at a very low temperature to be operational. And this is a very important contribution. The Planck detectors are now probably the coldest places in the universe, except a few laboratories on Earth. And this very low temperature, 0.9 degree over absolute zero, is achieved by this dilution cooler that has been invented in France. And this is what you see here. Here you have also an image of the detector, the HFI detector, and the test facilities that has been used to test and calibrate and validate all the performances of Planck, the high-frequency instrument. This is one of the contributions of France. I must also quote the large participation of the French industry, among which at the first place Thales and Air Liquide. Here is an image of Planck in test at the Thales site in Cannes. And after the launch, it is not finished. You have also, to provide this beautiful image and scientific results, it's very, you have to analyze the data. And this is a project inside the project. And this is achieved via a lot of people involved, and also you need also big computers. This is an image of the computers that are used in Paris. Just a few words about what I think were the keys for the success. I said it's a 20 years long success story. Activities on Planck, and in particular the dilution cooler, began in 1990 with R&D activities supported by CNES in French laboratories, and a patent 2 years later. And the first proposal for a CNES small mission, at that time it was called SAMBA, was put to CNES in 1992. It turned out that it was not such a small mission, and it became an ESA mission, and we are very happy of that. There has been a good cooperation between the science laboratories, the industry, as I said before, the space agencies and ESA, and a strong support for research organisms, universities and agencies. Just a few numbers to quantify this huge effort. I'm not going to give you the numbers of millions of euros, but if you wish I can. Of course, in France, we had the leadership of this high-frequency increment. There are now, at the time being, 10 laboratories involved, 6 universities, 2 institutes from the Centre National de la Recherche Scientifique and the Commissariat of Energy Atomique, more than 120 scientists, and more than 50 engineers and technicians. All these people are behind the results that you are going to see. At least in France. And we are very happy to see the first results released this week at the conference, and very eager to see the next set of data released next year and the year after. Thank you.
Thank you, Fabienne. Please have a seat. Good. We have been hearing now a lot about this early release of the compact source catalog, but well, at least I want to know what is in it. And there are a lot of things, but the details has now our project scientist Jan Tauber. He's the project scientist for the Planck mission at ESA.
Thank you, Marcus. So, as Marcus said, I'm going to tell you a little bit about the data that we are releasing today, the Planck data, which is the first data that we release, and I will introduce the next talks, which are going to concentrate a bit more on some of the scientific results that we are highlighting for you today. So this is a nice diagram which has been shown before, I think, and it shows the history of the universe basically on one view graph. And as was said before, Planck is a machine that is designed to measure the first light that comes at a very early time in the universe. And this light is called the cosmic microwave background. And we are very lucky in a way, because at that very early time, the light that was generated essentially propagates without perturbation to us. So that when we observe it, we are basically making a map of the universe as it was in a very early time. At a very early time, where the universe had very few features, it was extremely smooth in terms of its structure. And those features needed a lot of time to develop. And they developed over time basically through periods where matter concentrated increasingly and eventually became the structures that we see today. Now these structures also radiate light, and this is light that we can observe with Planck. And we can observe light that radiates from very early times when matter had not advanced very much into its structuring process, but we can also observe light from very late times when matter has evolved into the kinds of structures that we know today, like galaxies and clusters of galaxies. And when we make a map with Planck, then we see this very beautiful mix of things, which was shown to you before. And this map is particularly illustrative because it shows to you the cosmic microwave background, which is what we really want to see, but also all of this other light, most of which is the light of our own galaxy. And you can find, if you look closely in this map, a number of well-known features that we have observed before using other observatories. For example, the Magellanic Clouds, which are companion galaxies to our own galaxy, the Milky Way. We can see distant galaxies, both emitting radio waves and emitting infrared waves. For example, here we have Andromeda, which is a very beautiful, large spiral galaxy, which is not too far from us. And mostly, as I said, we see our own galaxy, the Milky Way. All of these lights, different lights, the cosmic microwave background, distant galaxies, and the closest galaxy, our Milky Way, they are all mixed up. And in order to make sense, to make science, we have to go through a process which we call component separation. We have to split apart these different components which are mixed up in the Planck data. And at the end of this process, which is basically a software process, we end up with different maps which contain different components. For example, the CMB, this is the cosmic microwave background. This is our ultimate objective, is one of the faintest signals in the sky, and therefore one of the most difficult to extract. This is not one, unfortunately, that we can talk about today, because we still need to work on the data quite a bit. Stronger signals, such as the galaxy, are a bit easier to extract, and I think if everything goes well, maybe in a year's time, we can come back to you with good results about our galaxy. What we are talking about today is more like this. This is a component that we call compact sources. These are basically sources that look almost point-like to our satellite. They are bright and they are very small on the map. So when we are able to do this component separation process and analyze the Planck data, basically our main objective is to do cosmology, that is, address some of the fundamental problems that we have in the universe, such as looking at its origins, looking at its contents, as it says here, probing physics at extremely high energies, but also looking for the earliest processes of structure formation, looking for the first stars and galaxies. But also, we can look at the other components. We can try to understand how the later evolution of structure is taking place. We can look at structures such as large clusters of galaxies, large filaments of dark matter which are slowly collapsing and will end up forming galaxies and clusters of galaxies. And we can observe the closest object to us, closest in space but also in time, our own galaxy. And the data product that we are releasing today, which is called the Planck Early Release Compact Source Catalog, rather difficult name to pronounce, but it's basically a list of these compact, bright sources that we see in the first component separation process that we apply to the Planck maps. And it's the first step in the direction that we are taking with Planck, which is eventually to come to this. So what does it contain, this catalog? Basically, it contains, as I said, a list of sources. There are about 15,000 of them. It contains mostly two classes of sources, sources which are inside our own galaxy. So if you look at that picture, you will see that they cover essentially the whole plane of the galaxy, but they also include many galaxies beyond our own, so both near and distant. It contains two very interesting lists of sources, scientifically interesting. One is to catalog a list of the coldest spots that we can find in our own galaxy. These spots are extremely interesting, both because they allow us to understand how physics is going on inside the medium which permeates our own galaxy, but also because these are the sites where stars are eventually going to form. And Planck is ideally designed to find and measure the characteristics of these spots. Don't forget, it's designed to measure the coldest object of all, the cosmic microwave background. As a byproduct, it measures low temperature clumps of dust and gas very, very accurately and effectively. And we also have a specific list which is dedicated to finding and characterizing galaxy clusters, which are one of the major building blocks of our universe, and we have a very specific technique to do that on Planck. Planck has been designed to do that. You will hear a bit more about how it does it in one of the next talks. Overall, this catalog that we are releasing today, that is available since this morning to the public, is really a treasure trove. I mean, it contains many, many possibilities for science to the community. And I would also add that it's a really juicy foretaste for what's going to come in the next couple of years. Here's just a brief overview of what the catalog contains. Here's a famous picture that you've all seen, and now we're going to overlay on it all of these 15,000 sources. As you can see, there's lots of them. They fill basically the sky. There are two particular classes, as I was telling you, extragalactic sources and galactic sources. Galactic sources basically follow the plane of our galaxy, but as you could see, they were also all over the filaments. Extragalactic sources, they fill the whole sky, basically. They are everywhere. And we can normally classify them into various kinds of galaxies. So this is essentially the product that we are releasing to the public today so that the astronomical community can do science with that. Now, we can do a lot of science with that, and with some of the additional data products that we are able to trust today coming out of this component separation process that I was talking to you about. Many of the results that you will hear about in the later talks have to do with the called the cosmic web. This is basically the interlinked structures of mass, basically dark matter, but also with normal matter mixed in with it, which is collapsing starting from the Big Bang and to our own time. And as it collapses, it makes this very intricate spider web of mass that we call the cosmic web. And you will hear two particular highlights here. First of all, how Planck offers us a very good technique to measure the integrated light from the galaxies that are forming along these filaments here. All of these points that you see here, they actually are forming galaxies. And when you see rather big clumps of them, these are what we call clusters of galaxies. Right? And with Planck, we have a nice technique where we can look at unresolved, so smoothed out emission from all of the structures that are forming here. But we can also look in detail at some of the specifics, some of the biggest nodes in this spider web of structure, if you like. And we have this specific technique that I mentioned before, and that will be explained in one of the next talks, that allows us to look at these largest building blocks in a lot of detail. You will also hear in one of the upcoming talks about our own galaxy and about some strange forms of matter that Planck is giving us new tools to investigate. For example, we are finding that there are these tiny grains of dust which are located in a large part of our own galaxy, which are spinning madly at really huge speeds, and they emit at very specific wavelengths. And Planck is allowing us to map these regions which contain these rather strange forms of matter. We are also uncovering matter which may have some rather strange properties. For example, dust which agglomerates in rather unexpected ways. And this you will hear about in one of the next talks. I was talking before about the special list which is concentrating on measuring, finding and measuring the coldest spots in our own galaxy. And unfortunately, we will not be able to have a specific talk on that because of time, although there will be people here after the talks whom you can ask questions about this topic, which is very interesting. But I want to make the point that this is the first census over the whole sky that is being made about these sites of star formation. And in many cases, we find clumps that are so cold that they really approach physical limits in how low they can get. And this is extremely interesting scientifically. So, to finish, again, looking from now to the future, we realize that in order to get to the final objective of Planck, which is to quantify and observe in detail this first light, the cosmic microwave background, we first have to understand everything that is in between. And Planck allows us to get the whole range of structure that is in between. The earliest structure that is forming, this cosmic web of dark matter and normal matter that is collapsing slowly on itself and forming galaxies and clusters of galaxies. But also the much later structure that is forming, the normal galaxies, and the whole zoology of galaxies that we know are out there with very active objects on the one hand, and also very objects which are very actively forming stars. And of course, I don't want to forget our own galaxy, which is our closest neighbor, and which is, in fact, if you like, the smallest of all the objects that we observe, but it is the largest in terms of how much of the sky it occupies. The data and the results that you will hear about in the next talks really are giving us the first concrete results in the direction of this investigation of the structure that lies in between the cosmic microwave background and us. I want to emphasize that it is really showing the high quality of the data that Planck is gathering. And it gives us a hint of what is yet to come. So, if you will watch this space, then in another couple of years we will be able to come to you and show you the cosmological results that will be the end product of this investigative journey. Thank you.
Thank you very much, Jan, for preparing us for the scientific talks to come. Take a seat over there, please. One remark, you saw the compact source animation there, where it was the black one, where you could see the different spots on it. You have this one also on your media stick. So if you need this one, this little video, it's on your media kit. Yeah. As we said before, it's the cosmic microwave background that Planck is after, but there are other backgrounds. One is the cosmic infrared background. And this, as I understood it, is basically the radiation that stems from the birth of galaxies and stars, but it's not direct one. It's absorbed by the dust in the universe and re-emitted by the dust. What this means for our understanding of stars and galaxies, this will tell us now Jolou Puget from the Université Paris Sud. and he has the details on the cosmic infrared background.
Thank you, Marcus. Yes, in fact, Planck, as you understand, is a very powerful machine to detect very small fluctuations of the radiation, which we call the cosmic background. I'm going to talk mostly about what we call the infrared background, which is a background which emerges at later time, but which also illustrates very well the powerful sensitivity of Planck. So, starting from this picture that Jan Tauber showed, when we look at the microwave background, which has been very well mapped by WMAP and Kobe earlier, we see the level of fluctuations and the structure of the very early universe. And this structure, especially the dark matter in it, will collapse under its own weight. And the theoreticians can make simulation of this kind, which shows how this matter is falling on its own weight along these filaments, and all these nuts is, as was said, a bunch of galaxies forming out of this gas. We know, in fact, in our own galaxy and from the number of infrared satellites which came before Planck, that active regions of star formation in our own galaxy, for example, or in nearby galaxies, we see the light emerging as mostly in the infrared. These big clouds of gas which are forming stars are very opaque. The dust in it make it opaque to the light emitted by the stars, and so it's absorbed by dust and re-emitted in the infrared. It seems that the same is going on at very early stage in the universe when the galaxies formed. In fact, they do transform very actively their gas into stars, and it happens that, in fact, the energy is also coming out very much in the infrared. So that's what we are after in that. Furthermore, observing individual galaxies in the infrared when they are very far away is difficult. The resolution, the sharpness of telescopes at long wavelengths is much less than what is, for example, the sharpness of the Hubble Space Telescope. And so, in fact, that's why we are looking at this radiation, which comes beyond what was shown, for example, also as observed by the Herschel Space Telescope. We will look at it as just the integrated light from many galaxies together. So, if we look at this cosmic background, which is what astronomers observe, which is coming from outside of the Milky Way, as a function of frequencies or wavelengths, you see that in the universe, the so-called microwave background is completely dominant. In fact, if we had eyes which could see microwave radiation, which is typically in microwave oven, or the one which is used in cellular phones, you would see basically a very bright sky, very uniform. That's what we are after, it has been said. I'm not going to talk about that. Later on, of course, when the galaxies are emitting, it fills the universe with the radiation from stars, mostly in the optical, for the typically radiation similar to the one we see from the sun, but also everything which has been observed by dust, especially in the very early stage of galaxy formation and star formation, radiates in the infrared. We are observing basically from this frequency to this frequency in 4 bands that I'm going to see. One thing I want to point out is in the lowest frequency band, you could see that this infrared background we are after is really very small compared to the microwave. And it's only because Planck is so sensitive and will map the microwave background with extreme sensitivity that we can detect, in fact, the fluctuation of that. And the fact that we could do it is really the proof that we know how to do it. In fact, 95% of the radiation is in there, and what we are looking is this 2.5% here. We went to look for this radiation into a small set of fields which are clean ones. So you see here the microwave background, and what we are looking is a small fraction of that at this wavelength, and we looked at it in this field, which are especially clean ones in terms of the foreground, in terms of the emission of our own galaxy. Each of these fields, in fact, is typically, if you look at the surface area of the moon in the sky, each of them is typically 100 times the moon size. So you would see changing with frequencies, these 4 bands, you could see that it's about the same. And when we go to the lowest frequency, it starts to change. And you see that when we are getting to 217, which is the lowest frequency, it's quite different from the original one. It will cycle through it, so you can see that it is changing. It's not changing very much in the first one. We see the nearby structure, which is not the more interesting. But when you get to the lowest frequency, you see different structure, which is really the more distant one we have not yet accessed before. So basically, we are at this frequency really looking at structure which are galaxies which are forming stars extremely actively less than 2 billion years after the Big Bang. And it's really the change of this structure which demonstrates that we are seeing this very distant layer. So to summarize what we have learned from that, we have learned that the process and history of gas gathering into galaxies and transformed into stars is really making a lot of its, radiating a lot of its energy in the infrared, as expected. We do see, in fact, the cosmic web, which is predicted by the simulation of dark matter, but we don't see the dark matter by definition, but we do see the stars form in them when they form. So we cannot see anything in between the time of the CMB, 400,000 years after the Big Bang, and typically 1 billion years after that when stars and galaxies form, and that's where we are catching here. So it's for the first time we can catch an image of that early of this structure in the galaxies. And at the lowest frequency, as I mentioned, it's only 1% of the microwave. So considering we can detect very well that, it gives you a hint about the quality of what we will be doing on the CMB 2 years from now. And what we can extract from this data is really how fast, in fact, the galaxy formation and the star formation happen in this phase. We know that individual galaxies, which have been observed by telescopes like Herschel and so on, do form stars at 1,000 times the rate of our own galaxy. And we are looking at it here on the large scale and see the full picture. So that's what we are extracting in terms of quantitative data. Thank you.
That looks good. We've been talking a lot about the compact sources, and I said in this catalog there are a lot of those things, and one of those things are the galaxies and the clusters of galaxies, and what Planck can contribute to the understanding of the clusters of galaxies. This will be explained now by Nabila Aghanim. She is also from the University Paris Sud, and she will have the details now on how galaxy clusters are forming.
Thank you. Okay, so good morning, everyone. Galaxy clusters are the largest formed objects. In fact, they're the largest dense objects that we know in the universe. And to go back to this cosmic web plot that you have been shown previously, the galaxy clusters are those very bright spots that you see here at the knot of the filaments of the cosmic web. From the observational point of view, galaxy clusters are some type of contents, 3 contents. Galaxies, this is what they're called, galaxy clusters. They're observed traditionally through the, I would say, concentration of galaxies in the sky. And galaxies contain something like hundreds to 1,000 of galaxies. They contain very hot gas, very, very hot, tens of millions of Kelvin. And they contain dark matter, which consists of 80% of the mass. So they're dominated by the dark matter in terms of the content. As I was mentioning, those objects are formed at the knots of the filamentary cosmic web, and they're formed out of the flow of matter along those filaments. Galaxies flow on the filaments and form the largest object that you see here, which are the clusters. However, they originate from initial cosmic seeds, those cosmic seeds created at the infancy of the universe, and of which the CMB gives us the first image. By those properties, they're located at the cosmic knot, they're produced out of cosmic seeds, produced at the infancy of the universe, makes the clusters the best witnesses of how the universe has formed and how it evolved. So there really are cosmological probes that we use for our understanding of the big picture of the evolution of the universe.
Sorry, what is a cosmic seed?
Sorry?
What is a cosmic seed?
A cosmic seed is a small perturbation of matter which has been generated at the inflation time and which through gravity is forming, evolving, getting more and more massive to form the objects. So it's really a seed in the sense that you put something, it grows, and it gives a galaxy, a cluster, name it. So traditionally, they're observed through as I was saying, concentration of galaxies in optical, and then probing the galaxy content. However, as I was mentioning, they have very hot gas, which is observed since 20 years already in the X-ray domain by X-ray observatories, and it probes the gas content of it. Since very short time, we've been now able to observe in the microwave domain this gas, and in fact we're observing it even better with Planck through the so-called Sonia-Evzeldovich effect. I will make it simple, and it's really behind this very complicated name is a very simple physical process. The photons of the CMB, the light of the CMB, the first light that we were talking about, traverses the matter, traverses the filaments, and traverses the knots. So it traverses the galaxy clusters. And when it goes through a galaxy cluster, the photons of the first light get kicked by the hot gas, by the electrons of the hot gas. They get kicked, they gain energy, they got hotter, and they are displaced from the low frequency region of the electromagnetic spectrum to the high frequency region of the electromagnetic spectrum, creating what was forecasted in the 70s by Sonia-Ev and Zeldovich, creating holes in the sky. And in fact, it's exactly what we see with Planck. We see holes, we see a central spot in the direction of one of the galaxy clusters, which appears blue here, the spot, the cold spot, the dimming of the CMB light at the low frequency, and it gets brighter at the largest frequencies. It's really this effect, very simple, kicking the photons when they go through hot gas, which makes it easy and interesting and unique, the Planck instrument, which goes and observes the whole sky for those coincidences between regions where the light is less bright and regions where the light is bright, and to measure the clusters. With this effect, the Sonia-Evzeldovich effect, this kicking of photons, Planck is providing to the community the largest cluster sample observed in the microwave. It's a sample of about 200 clusters. 30 of them are new clusters. The rest is already known clusters that we are observing for the first time in the microwave domain. Planck has the ability to cover the whole sky, and through this to detect the rarest object, the most massive ones, those which are the most, I would say, interesting for the cosmology, as they trace the knots of the cosmic web or the whole sky. They reveal the cosmic seeds and basically help us in probing the cosmological models. How do matter form, and how did it begin? In addition to the discovery of the clusters by the Planck satellite, we are having with the Planck data a brand new view of the hot gas in clusters. This brand new view is first of all telling us that there is an agreement between the properties of the gas that you see here in X-rays and the properties of the gas that you see here through the microwave, and this is a Planck image. This is a Rosat image of one of the largest clusters in the sky. This cluster has 4 times the size of the full moon on the sky. Planck is telling us as well and learning us and opening questions as well on the relations between the galaxy in the cluster and the hot gas, and shedding light on the intricate process by which galaxies flow in the filaments, and by which the gas, which is not yet formed in term of galaxies, is also flowing in the objects. Planck is discovering new type of clusters, I would say, and this is a gallery of the clusters. This is a gallery of the clusters, new clusters that were confirmed by XMM Newton and discovered by Planck, showing us that we are now starting to reveal a population of new clusters which are still forming. So clusters at the infancy, still merging in the process of assembling the matter towards the most massive ones. Moreover, Planck is discovering very funny systems and very interesting and rare systems. Planck is discovering superclusters, which are gathering of clusters, of which, to date, only 20 are known and named, about 80 may be observed through optical surveys, large optical surveys, and Planck is really starting and having for the first time a new tool to detect them. So Planck is is providing the first all-sky galaxy cluster survey after 20 years. The last one was provided by the Rosat X-ray experiment. We're discovering new clusters that are still forming, young clusters, I would say. We're revealing the clusters from the lowest masses to the highest masses, which allows us to image the cosmic knots all over the sky. And most of all, we're opening up a brand new observational window in the microwave to study and to understand the clusters. And thank you very much.
Thank you, Nabila. Please have a seat. We are coming now to the last presentations, and from superclusters to very, very tiny small grains. And Planck was not only discovering clusters, but also other things. For example, there's something called the anomalous microwave emission. So we know it's there, but we don't understand how it can be there. Planck took a closer look and found out how that happens. And another thing is dark gas. Dark because we couldn't see it so far, but Planck again took a closer look and found out what it is. The details has now Clive Dickinson from the University of Manchester.
Thank you, Marcus. Good afternoon. We're coming a bit closer to home now, from millions of light years and billions of light years down to hundreds of light years in our own galaxy, and in particular two mysterious components of our Milky Way. Mysterious in the sense that we really don't know much about these components, and Planck's unique sensitivity, all sky mapping ability, and wide frequency coverage is really helping us understand what these components are. So the first one is, as Marcus says, it's called anomalous microwave emission, or AME for short. So it's called anomalous because we really don't know what it is, although we think we have a good handle of what it is now, especially with Planck data. And there's two key facts about this anomalous microwave emission. The first fact is that it's only strong, you can only see it, in a fairly narrow range of frequencies, sort of 10 to about 100 gigahertz. It's particularly strong between 10 and 60 gigahertz, peaking at about 30 gigahertz. And that's perfect for Planck, because Planck covers that frequency range. The second important fact is that it's very closely correlated with dust grains that Planck also sees with its high frequencies. So it seems to have something to do with dust, although it seems to emit in a frequency range that is not normally associated with dust at lower frequencies. And as Marcus said, what we think is happening is that this is due to electric dipole radiation, which is a complicated name, but often people refer to it as spinning dust grains. These are very small grains that spin so fast, they end up being essentially radio transmitters because the electrons and the charges in those grains spin so quick they emit radio emission. But you have to spin them extremely quickly. And that's the big surprise. Although, if you delve into history books, you actually find that this was proposed back in 1957 by Bill Erickson. You can see here. Quite amazing that it was proposed all that time ago, and it was largely forgotten about until the late 1990s. That's when it was first detected by CMB experiments operating this frequency range. So what do we see with Planck? Well, here we have some maps. The first 6 panels are Planck data, going from low frequencies. This is 28 gigahertz, the lowest frequency channel of Planck. And we go to higher frequencies as we go along here. This is 44 gigahertz, 70 gigahertz, 100 gigahertz. And then we get to the highest frequencies with Planck, going all the way to 857 gigahertz. And what we see here is we see all the structure in the dust at the high frequencies of Planck. This is normal thermal emission from dust that we know quite a bit about, and Planck is really helping us to understand the cold part of that dust. But what's happening here is that as you go to lower frequencies, that thermal dust tails off. It becomes fainter and fainter as we go down here. And you can see here there's not much emission here at 70 gigahertz. But as you go to lower and lower frequencies, it suddenly becomes brighter again. And that's the surprise. The fact it's so bright at 30 gigahertz. And we think this is due to these very tiny grains spinning very quickly and emitting at 30 gigahertz. And when you go to even lower frequencies, using data from radio surveys taken from the ground, you don't see this emission. You can see here, the bright blob in this ellipse here, you don't see it at low frequencies or in the optical. That's why we think it's not normal emission that we're used to seeing in the radio and optical. It's something new. So where do we go from here? Well, we're astronomers, we like to make spectra of things. So we take this ellipse and we add up all the signal in that ellipse and make a beautiful spectrum. And here is spectrum of one particular region. It's the Perseus region that I've just shown you. It's about 700 light years away in our spiral arm. And we can get the entire spectrum all the way from radio wavelengths, this is near 1 gigahertz if you like frequency, all the way up to 3000 gigahertz over here. And Planck fills this gap all the way from 30 up to 850 gigahertz. So it's the only way we can see this thermal dust tail here. And we must subtract that and the radio emission to see this excess emission. It's this emission here, this bump. That is the anomalous microwave emission. And what we can do now, because of the Planck data, is subtract the other emissions that are emitting in this region. So it's this stuff down here and this stuff up here. And we can make a spectrum of just the anomalous microwave emission. That's this thing here. And the amazing thing is that the theoretical models of spinning dust grains, you can make them fit very easily. You can make them fit the data perfectly. You can see here the curve. That's a fit to the data using a theoretical model of the spinning dust using environmental parameters for this region. It's not just a sort of ad hoc fit. We're actually using the environmental parameters that we know for this region to fit. So it all seems to work very nice. And I think this is the best spectrum of spinning dust to date. And the Planck data has really allowed us to do that for the first time. So let me move on to another mysterious component. This is the so-called dark gas. Now before you jump up and down, it's nothing to do with dark matter or dark energy. It's a sort of unfortunate name that we've stuck to now. It's dark gas in our galaxy. It's not dark matter. And it's called dark gas because it's something that isn't traced by normal traces of the interstellar medium. We're astronomers, we like to split the components up, as Jan said, into its constituent components. And what we normally do in the interstellar medium, the gas and dust that's in our vicinity, we split it up into the atomic and the molecular part. And the atomic part you can get from the neutral hydrogen. If you measure the neutral hydrogen, that gives you the atomic part. And the molecular gas you can trace using CO, because CO produces bright emission lines in the submillimeter, and you can detect those and map them. Now let me see if I can explain this graph to you. So that's rather complicated, but basically the horizontal axis is an estimate of the density from the atomic gas, which is this neutral hydrogen, traced by neutral hydrogen, plus the gas traced by CO, carbon monoxide. And if you do that and compare it with Planck data, so this is Planck data, essentially intensity, this should be proportional to the density of the total interstellar medium. Dust is a good tracer of the total mass. And what you find is, if you look carefully, is this red line here is the model fitted at low density, so on the left side of this graph. And you can see the data follow this red curve very nicely, these blue dots. But what we then find is that at intermediate densities, as we move to the right, there's this excess, this bump above this model. And then at very high densities, it comes back as onto the fit. It's this excess here that is the dark gas. And basically what it is, it's gas that it does not have strong hydrogen and strong CO. In particular, it doesn't have strong CO. So that means it's probably molecular gas that consists of something else but not CO. And what we think is happening is probably got a significant fraction of molecular hydrogen, not atomic hydrogen, but molecular hydrogen, H2. And with Planck, we're doing this separation. We can actually map this out now and make a beautiful map like this. So here this is showing the excess emission, which we attribute to dark gas. And this is traced by Planck data. This is thermal dust data, tracing that dark gas. And what we find is it fits our expectations perfectly. Basically, we see a lot of excess in these star-forming regions that Mark showed before. For example, low Fucus, we see an excess of this dark gas. And this fits into this picture that it's molecular hydrogen. Probably what's happening is that the intermediate mass stars are producing UV light, which is destroying the CO, but it's not powerful enough to destroy the hydrogen, the molecular hydrogen. And so you see it in these regions, these star-forming regions, such as low Fucus, and you see it down here in Orion, and here in the Polaris flare as well. So we're getting a proper first look at this new component of the interstellar medium. And of course, in the future, we'll be able to compare this with all the other data that we're gaining with Planck and try to understand this component in more detail. Thank you.
Thank you, Clive. Please have a seat. I think there's a lot of meat in for you, but you might have some additional questions. That's the reason why I was asking the ladies and gentlemen to take a seat. If you have questions, I would like to ask you to give us your name and the media you're working for. But it's not only that our presenters will be ready to take your questions. We have also somebody from Thales Alenia Space here in the auditorium. It's Jean-Jacques Juillet. So if you have a question about the space industry, who built Planck, actually not only Planck, but also Herschel, we have somebody who could answer those. Then the science teams are almost all here, so we can even go into detail if you wish so. And please, are there any questions?
Hello, thank you for taking this question. My name is Mark Vosier. I'm a freelance journalist, but today working for Associated Press. Can you please explain this to me, because I'm not a scientist. Is it right that today you're announcing that 30 new clusters of galaxies have been discovered as a result of Planck?
Is it? Yeah, it's working. Yes.
Good.
This is a short answer.
All right. And so before that, there were...
Well, let me go more into the detail. The early compact source catalog, out of which the SZ sample I've been presenting is part of, has been produced. In fact, it has been produced with our US colleagues. You have Ranga here next to you, responsible of its production. And it has been produced in order to allow the community to have the opportunity to follow up, observe further objects, which may be clusters, which may be galaxies, which may be galactic clumps and things like that. So what we are announcing is that we have 30 objects, 21 of which have been already confirmed by XMM Newton observations within the Planck collaboration, internal confirmation. One of them confirmed with the AMI interferometer, and the rest is to be confirmed.
Okay, and so before that, we knew of 169 clusters, and they were only discovered through optical telescopes?
So by having this ability, Planck having this ability to observe the so-called Sunyaev-Zeldovich effect, this kicking of the photon of the CMB photons, we're able to detect, I would say, blindly, directly, without any prior information on the clusters. So what we've been using is that we have used only the Planck data and Planck maps, and we have spotted those about 200 objects, out of which a posterior analysis has shown that 169 of them were already known.
Okay, last question if I may. You said that, or somebody said that about 380,000, billion years, I can't remember, just after the formation, just after the Big Bang, that stars were being formed about 1,000 times faster than in our own galaxy. What does that mean? Does that mean that like one new star every day or one new star every month? What does it mean?
Well, just recording the numbers to start with. We see the structure in the so-called microwave background, which is propagated freely from about 400,000 years after the Big Bang, 380 exactly. And then we lose any way to observe it because basically the matter is propagating freely and the radiation is propagating freely, and the matter is in a state where it does not radiate. It's mostly dark matter and cold ordinary matter which doesn't radiate at all. And we catch again this structure after a long time where they basically concentrate under their own weight, typically 1 billion years after the Big Bang, much later, but when the universe was typically 5 to 10 times smaller than it is now, with the first galaxies. Now, of course, the gas has to be transformed into stars for us to see it. So we don't see, we see basically the galaxies when the first generation of stars are already formed. And as I mentioned, we see them in the infrared more than in the visible for the biggest part, because we know that star-forming regions do radiate mostly in the infrared because of the opacity of the cloud of gas as soon as stars are formed, because they form dust also. And so what I was saying is basically we are trying to get as close as possible to the formation of galaxies and catch the structure at this time.
Here's another question.
Marcus, can I just...
Okay.
Can I just...
You have it in front of you, Marco.
It's not working. Oh, is this one working now? Just to address the question numerically, our Milky Way galaxy forms a star about the mass of the Sun, 1 a year. So to answer the question directly, if you like, it's 3 a day, is 1,000 roughly. Okay. So, but these galaxies are rather different to the galaxy we live in today. So it's not an easy thing to, compare the modern day spiral galaxy with these forming galaxies. But as a point of scale, our galaxy, 1 star of the mass of the Sun per year. Of course, they're not all the mass of the Sun. There are smaller ones and bigger ones, but as an average.
Just can even say that you built, in fact, it's another way to measure it, and I should have said that. You build the whole set of stars in a galaxy, basically in 1 billion years, 1/10 of the age of the universe. It doesn't build over the 10 billion years. Most of it is built in a much shorter time.
Hello.
Sorry, just to be clear,
Jean,
sorry.
may I?
Yeah, let me just, because there may be a confusion here, of course, as Fabienne has pointed out. It doesn't take a day to form a star. It doesn't take a third of a day to form a star. It takes 1 million years. It's just the production rate is something like 1 a day or 3 a day in this case. Just in case anybody gets confused, it can be done quicker in the early years.
Okay. Jean-Pierre Martin from l'astronomy. I have one question concerning this beautiful picture of the full sky. There's something bothering me. This is this foreground of our galaxy. When are you going to remove it and give us some information? Yeah, I know you're laughing. Is it still on embargo? And when are we going to have real information on CMB from Planck? And second question, any idea of the polarization of the CMB? Sorry. Yeah.
So these are hard questions that you're asking, and as I tried to say in my presentation, it takes quite a lot of work to make this component separation to the accuracy that we want. The cosmic microwave background signal is extremely faint, and if we want to get it accurately enough that we can really do science with it, then we need to work on the calibration for quite some time. And today what we are delivering is basically the best product that we can produce for small structures and small fields. And we have committed to deliver the data related to the cosmic microwave background and so on in 2 years' time.
So it takes shorter than a starter form.
For sure, for sure. Polarization is a hard problem, and we, as I said, we are also committed to deliver that in 2 years' time, and we are sure doing our darndest to do that.
Can I just maybe giving you not the answer you want, but at least go one step further. What we know today is that the basic sensitivity, even for the polarization, is basically what we aim for. In an instrument like that, to get the cosmology out of the microwave background itself, we need extremely accurate and clean data. And it's really the cleaning from systematic and instrumental effect, which is still not done. We have done, obviously, from the data you saw, component separation to extract the foregrounds, and even for the CMB, we have removed for the CIB, for the infrared background, we have removed the microwave background. But we didn't need for these to extract science and very useful science, we didn't need the same accuracy. So that's the accuracy we need in the determination of the maps and the structures, which really makes this 2 years delay that Jan was talking about.
No, it's not a delay. Not a delay.
The time it takes to do it. So
it's what we expected it would take. And okay, I mean, some people would claim it would take. We should take longer time. But we, as Jean-Loup said, all of this process we can do today. The thing is that before we release to the public and we do real science with them, we want to be absolutely sure that it's the cleanest product that we can do.
Okay, here comes the next question.
It's Jonathan Amos from BBC News. I've got a couple of questions. Nabila, if I can start with you first of all, can you give us a sense of scale? I mean, you've seen some of the largest structures in the universe. Can you tell us how big, to a layperson, just how enormous are these things?
Well, so in fact, the largest scale of the observed universe is the one that you get out of the CMB. Then you have the big voids, big walls, comes the supercluster scale, comes the cluster scale, and the cluster scale is something like 10 to the 7 light years scale with respect to the cosmic hierarchy. So these are really the largest, I would say, formed, gravitationally formed objects.
This is about 10 million light years across, yes?
Yeah.
And so you've seen clusters or superclusters?
And superclusters.
You've seen clusters
both
and
of them.
superclusters.
So basically we've seen the two largest formed scales in the universe.
Okay.
And and by tracing the knots, we may have an insight on the walls, the filaments, the cosmic web. But this is for the future when we will release the CMB data as well.
And then a couple of questions for Jan. Could you update us on the status of Planck, your cryogenic resources, how long the mission has, even beyond, I think, your 4 times coverage?
Well, we're pretty confident today that we can operate Planck until the end of this year at least. How much we go beyond that will depend, in fact, on the cryogenic coolers, whose lifetime is not so easy to predict at let's say, with a precision of order a month or so. So I can say that we will have the full payload working with high likelihood until the end of the year, which should give us 5 full sky surveys. And whatever we get beyond that will be a bonus, a real bonus.
And then I'm intrigued. I mean, how do you lock this down? Given the Nobel Prizes that have been won in this field, how do you keep this data secret? Because even some of it could be applied to WMAP data to confirm things that people had an idea about, but they can only say with surety when they've seen some of the Planck data.
Yeah. Well, I think the way we keep the data secret is because the reason we can do it is because people are convinced that this is necessary in order to allow us to do the best job we can. The people in the teams are convinced. We don't need to convince them that that we need to keep the data, let's say, proprietary for a certain period. But this cannot last too long, of course.
If I may add, it's not about keeping the data secret. It's about making sure that we have the best product ever, as was mentioned by Jan. And this takes time, some time, the necessary time.
Any further question? Yes.
Mike DeVernon from Aviation Week. I just wanted to follow up on Jonathan's question. I believe you said that the low-frequency instrument will remain in operation longer than the high-frequency instrument. Could you go into a little more detail on that?
I didn't say that, but you know that, obviously. So let me elaborate on that. We have a rather complex chain of coolers that is cooling both instruments. And the high-frequency instrument, which is the bolometer, based on bolometer detectors, this is cooled to the lowest temperature on the satellite. And it has a specific cooling system that runs on cryogenic gas that is stored on board and which is exhausted to space. So at some point it will end. And this is why I'm saying that we are pretty confident that we can run the system until the end of this year, because that there is enough gas for us to run that cooler until then. For the LFI, we don't need this gas-based cooler, but we use a different cooler, which also has a limited lifetime. But it could live longer than the end of next year. So there is a possibility, let's say a fairly high probability, that beyond the end of this year we could be operating only one of the two instruments, the low-frequency instrument.
How long could that LFI last?
That's a good question, and I wish I could answer it with high certainty, but I think what we are hoping for is 6 months.
Just a quick compliment on this lifetime for the high-frequency instrument. In fact, we measure every day the temperature and the pressure in the two tanks, which are containing the helium-4 and helium-3, which are driving this cooler, which is called a dilution cooler, by mixing the two isotopes, and which was mentioned by Fabienne Casoli earlier. And so we see the amount of gas we have decreasing slowly, and we measure basically at the rate we are using the gas, how much time is left. And it has been quite stable, and that's a relatively, we have a relatively accurate measurement of the lifetime. In fact, it's basically January 2012, and it fluctuates by a couple of weeks with the measurement. It doesn't drift. So in fact, it's really what Janis said. We are pretty sure of that, which is much more difficult for the other one, as he said.
Any other questions?
Thank you. My name is Paola Antolini. I am independent. In this case, I am writing for the financial newspaper of Italy that is named Il Sole 24 Ore. So congratulations to everybody. It's a very exciting moment. If I can also congratulate especially Nabila, being a woman and also so young and so clear in her presentation. I just would like, because I am basically an anthropologist, and also because I am writing for this kind of a Financial Times newspaper, to have clear two aspects. First, how many man-years or human being years of work Planck represent today. And then, of course, we understand and we respect this secret attitude because the results are wonderful. is there the possibility to have just a clear summary of the discovery of Planck that you represent today? Because if I remember, is this well, I prefer to listen to double check if I understood everything. Okay, thank you.
So you took away my last question, which would have been to ask Jan to give us a wrap-up, in a nutshell, what we can take home today. But coming to the first question that you had, man years, who's going to answer this one?
I'm not sure that I can answer it. I mean, there are so many thousands of people have been working on this project. It started as a real project in 1992-93. So it's almost 20 years that it's been going. It's a large project of the European Space Agency. It has involved a huge industrial effort in Europe and elsewhere, a huge scientific effort in Europe and elsewhere. And counting that, I don't know.
5,000 or several thousand.
Yes, at least, I would say, at least.
Okay, before I would really like to ask you to wrap up, are there any other more detailed questions that you would like to ask? No, good. Then Jan, in a nutshell, what was presented today?
That's a difficult job. First of all, I hope you're suitably impressed, because Planck, it's a wonderful machine. It really is. It's a machine that's designed for a very specific purpose. That means that it has very special characteristics. It detects light at certain frequencies. It has a certain, let's say, sensitivity, because it's designed to measure very faint radiations, and it's designed to measure very cold objects. Okay? So it's designed to measure the cosmic microwave background, but on the way it gives us some very specific characteristics to do a whole range of other science. Now, we have selected a few highlights of that science to be presented here, and I can wrap those up maybe. But I want to point out there is much more out there. We're putting 25 scientific papers out, and I think they're all good, wonderful science. Okay? Now, what we've seen today basically is that the science we're doing today is concentrating, if you like, on structure between the early days of the universe and us. And we're concentrating on structures which are small on the sky. So either compact sources, which look almost point-like to Planck, but also small fields of the sky. And this is what we feel we can analyze with high accuracy today. Okay. And these are giving us a view of the structure in our universe at very different scales, curiously enough, because a small field on the sky today gives us quite a large view in the distant past. And what we've seen, for example, is that we are getting the first images of clustering at early times in the cosmic web, when these filamentary structures really are collapsing. And we're also finding that we can look at individual objects which are the largest nodes in that cosmic web, and we can look at them as individuals, not only in an integrated sense. And one of the things you should realize about Planck that was emphasized by Nabila is that it's an all-sky machine. And this gives you the ability to do statistics. I mean, if people have been able to observe clusters at these frequencies before, yes, but in very small bits of the sky. Being able to get the big picture is very important. And as Nabila says, it allows us to find new things, the superclusters, new objects, interesting, really interesting stuff. Then, of course, we've also talked about the nearby, our own galaxy, and we see how it is, in this case, the extreme accuracy that we can get with Planck that allows us now to make a very detailed accounting of all the components in the interstellar medium. You know, the ability to really measure very accurately very cold objects, which we did not have so far with astronomical observatories, to measure their temperature very accurately. This is telling us a lot about the interstellar medium, and it's allowing us now to, let's say, get some confidence about some of the components like the spinning grains in the dark gas that we could not really say much with previous observatories. There's a wide range of other results out there which I cannot wrap up because we have not presented them to you. Let me say, to kind of end up, for the Planck community, this is a big day. I mean, this is, you know, it's huge for us to release data, and it's hard for us to transmit the excitement that we feel. It's hard sometimes to explain the details of the science that we're presenting because there's a wide range of it, but we want to explain it. So I would like to say, take the opportunity. We're in the middle of a conference about Planck and about other topics. There's lots of scientists around. Take the opportunity, go and talk to them, ask us questions. We want you to be as excited as we are.
Referring Jan was referring exactly to the scientific conference, which is almost in the basement here in the building, and we also have been arranging for something to eat for you. So if you feel the need, please come along with us and enjoy the environment there. That would have been one logistic information I want to give you. The other one is, if you want to conduct individual interviews, please contact myself or Paul Hwistendahl over there, and we will bring you into connection with the people you want to talk to. And then there is something else. There's a bonus track for all those who have been asking themselves, why are we here in the planetarium? Because we have an absolutely stunning, beautiful film on Planck, which we will show at 2. So if you still have the time and you're still around, please come back. We will use this planetarium to show you this film. For the rest, I would like to thank our presenters. They did a fabulous job, and I would like to thank you for being here, and I hope you will stay with us and with Planck. Thank you very much. And the TVs should please come to Paul.
Hello, I'm Patrick from Module.